Okay, so here we are. It's section 2.41, maximum likelihood and sufficient statistics for the exponential family. And because this is actually quite a short section, we will actually combine it with the next one, which is on conjugate priors. Okay, so the very first thing we want to look at is actually a really interesting property of the exponential family, where the moments of the sufficient statistics, as u of x, are related to the gradients of this normalizing function, this partition function. So let's see where that comes from. You'll remember that for the exponential family, we had this condition that, well, we had the form of it, right? It was p of, x given eta. It had some, function h of x. And then there was a g of eta, and then there was an exponential of eta transpose u of x, right? And we know that this thing has to integrate to 1, so p of x given eta dx, so 1 equals this, is equal to, and we can take the eta out, and we get h of x, exp dx, right? So that's kind of a condition on that, and that's why we call this the normalizing the normalizing function, a partition function, whatever, because it is what makes the probability distribution integrate to 1. So without it, this integral over here might not integrate to 1. So we just multiply by this to make sure that it does. Now, so that's this equation 2.195. Now, if we take the derivative of both sides, and I don't have any intuition about why this is something we'd want to do, so I'm just going to take you through it and just to state the result. I think there's, what we're going to describe here is, I think it's actually probably, I think it's a deep property of the exponential family, and I think it has connections to equilibrium distributions in physics. So if any of you physicists are watching this and have some insights, please let me know in the comments. And if I ever come up with if I learn more about it and get some of those insights, I will share them with you. But right now, we'll just go through the calculations and just state the result as it is. Okay, so all we're going to do is we're going to now differentiate this expression, both sides of this expression, with respect to eta. So what's that going to do? So let me write it more nicely. So now I will zoom in so we have a bit more room. Okay, so this thing, what is that? So that says that g of eta integrating h of x times exp eta transpose x dx is equal to 1. So now if we differentiate both sides with respect to eta, well, so the right-hand side we know it's not equal to 0 because it's just a constant. The left-hand side is the fun bit. So this is the gradient of g of eta, and then so that's that, times this integral, plus g of eta times this integral. H of x doesn't do anything, so I'm just going to call it h. The exponential, it is left unchanged, but now we get this and this should actually be u of x. So this should be u of x. So because we have to differentiate eta transpose u of x, and the differential of that, when you differentiate that, the answer becomes u of x. And you can work it out in single element, or you can look at an earlier video I had on differentiating functions of vectors to figure out where that comes from. But if you can just do it element-wise, and you'll see that that's actually the case. So now you'll get d of x equals 0. So and that's where this expression comes from. So literally all you do is just differentiate this condition, both sides of it with respect to eta, and you get two terms. So on the right-hand side, you get the 0. On the left-hand side, you get a gradient of g of eta multiplying this integral plus g of eta times that integral, except now you've got this u of x inside. Okay, and then we're just going to rearrange this. So we move, I guess we're going to move, what is he doing here? He moves this to the right-hand side, and then we divide by g of eta. So let's just do that instead of instead of guessing, let's just do it ourselves. So now we are going to get gradient of g times this integral is equal to minus g times this gradient, and I'm going to add the u of x dx because that's the only difference, right? And now we're going to get gradient of g divided by g. Am I missing any signs? I don't think so. Is going to equal to, now we have this integral of u of x dx dividing by the integral itself, right? And that's just going to be, you can think of this is exactly the same as, this is going to be, just call this, all this stuff in dots, in ellipses, which which is actually all of this. I'm just too lazy to write it out. Well, you can think of that as the probability, some probability distribution, and an unnormalized probability distribution over x, right? So we're going to call this, so this is going to equal to, let's just call this, p of hat x u of x dx divided by, and we'll just normalize it. Okay, and that's coming from, so that's the top and that's the bottom. So essentially what we're doing is, this now becomes a normalized probability distribution. So this is just going to be equal to, let's just call it p of x times u of x dx, which is the same as just the expectation of u of x. Okay, so that is how we have gotten this expression here. So this thing is this, and it's equal to that thing. Okay, so which is what we have there. So he says, and then he says, so where we have used 2.1194, that's just the form of the just the form of the exponential family. We therefore obtain the result this. Now, where does the left-hand side come from? Well, that's just simply because if you have log of g of eta, then the gradient of this is going to equal to 1 over g of eta times the gradient of. So that's essentially what we have, except for the minus sign. Okay, so all he's saying is note the covariance. Okay, so we've therefore obtained the result, and let me erase some of this stuff that we have here to make it a bit easier to see. So we therefore obtain the result that minus the gradient of ln g of eta is the expectation of u of x. So and there's an exercise here showing that the covariance of u of x. So here we've now expressed the expectation of this function u of x in terms of the gradient of this normalizing function. That's kind of cool. So here we've kind of connected the data to the parameters in this kind of one-to-one way. And note that the covariance of u of x, so here's just expectation, can be expressed in terms of the second derivative of g of eta. So if you just take the first derivatives, you get the expectations. If you take the second derivatives, you get the covariances, etc. There's an exercise 2.58, which you guys should try to see that. Thus, provided we can normalize the distribution from the exponential family, so if we have this thing, we can always find its moments by simple differentiation, which is pretty cool. And I don't have any intuition for why that should be, so hopefully some of you do, and you can tell me and tell the rest of us in the comments. Okay. Now consider a set of independent, identically distributed data denoted by x. So we've got x1 to x of n, for which the likelihood function is given by this, right? So we're just they're all independent, so we're just going to multiply a bunch of probability distributions in the exponential family. So each of them is going to contribute this h of xn, and notice that, and that could be different because the data could be different. So we get this product, but g of eta is the same because they're all coming from the same distribution. So you get a g of eta to the n. And now you're just multiplying all these exponentials. They all involve terms where eta is transposing into a u of x. And then when you multiply the exponentials, you end up getting a sum inside a single exponential, and then you can just collect the terms of that sum. So you get this. Okay, setting the gradient of ln with respect to eta to 0, we get the following condition to be satisfied by the maximum likelihood estimator eta ml. So let's just have a crack at that. So the first thing we'll we'll do is we'll just take the log. So ln p of x given eta, and we'll just drop the terms that don't have eta in them. So this thing is going to contribute some terms, but we don't care, is equal to dot 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 plus n log g of eta plus eta transpose sum, right? And then if we just take the gradient, so gradient of ln is going to equal to 0 plus n over g eta times gradient plus sum on u of xn, because the eta drops out when you take the gradient. And so now when we set this to 0, goes to, we get minus the gradient is equal to 1 over n sum. And for the same reason as we saw up here, we get this is equal to minus gradient of log. Yeah, I guess I didn't even actually. So I've actually I would now be going back to this form. So I didn't have to do this step, but anyway. So minus the gradient of log of g of eta is equal to 1 over n sum of the contributions of that u of x from each the average contribution from each of those data points. Okay, so that's where we get this expression from, and let me erase everything else. Okay, which can in principle be solved to obtain eta of ML. So the point is that, yeah, we don't have kind of a closed form necessarily, but you can use some numerical techniques if you need to figure out what eta ML corresponds. So you have this. So this is just some number you'll get from your data, and then and you have the form of g. So you'll just need to figure out which eta. You'll need to figure out where its gradient equals this particular value, which you can do using numerical techniques if you need to. Okay, we see the solution for the maximum likelihood estimator depends on the data only through, so this is really important. This is a really important property. We therefore call it sufficient statistics. So we see the solution for the maximum likelihood estimator depends on the data only through sum on n u of xn. So this is the thing. So your data is not showing up necessarily by itself. It's showing up through this u function. It's the average of these sufficient statistics, which can be really cool. So it can often mean that you don't have to keep your millions of data points. Maybe just one summary statistic from each of them. One summary statistic is enough. So we do not need to store the entire data set itself, but only the value of the sufficient statistic. And we saw that. So for the Bernoulli distribution, for example, the function u of x is given just by x, and we saw that in the previous video. So we need only keep the sum of the data points x of n. And that kind of makes sense, right? If you want to figure out, what is the probability that a coin is giving up heads, well, the natural thing to do is to just add up how many heads you've had. And what's really interesting about this is that it says that that's all you need to store, because you might be like, well, maybe I need to figure out how many heads in a row I got or something like this as well. And actually, as it turns out, all you need is just the sum of the number of heads you got for the Bernoulli. So that's really cool. So we need only keep the sum of the data points, whereas for the Gaussian, so we should keep both the sum of xn and the sum of xn squared. So and that makes sense for the Gaussian, right? Because the Gaussian has two parameters. One of them is a mean, one of them is a variance. So it kind of makes sense that you need kind of the x of n to, let's say, give you a sense of the means, and maybe the xn squared are going to tell you something about the variance. But the cool thing is that all you need to keep is just their sum. So if you have millions of data points, all you need is just these kind of these short summaries, right? The sum of x of n and the sum of x of n squared to tell you what distribution they're coming from. You don't need to keep the entire data set that you've received. And this is if we consider the limit n goes to infinity, then the right-hand side of 2.28 becomes the expectation. So we're kind of getting back to this result. Then the right-hand side becomes the expectation of u of x, and so by comparing with 2.2.6, we see that in this limit, eta ml will equal the true value of eta. So as you get more and more data points, your eta ML will actually, your maximum likelihood estimate will approach the true value. I believe that's called a consistent estimator. I think that's what that's called. An estimator whose value approaches the true value as the number of data points goes to infinity. Okay. In fact, the sufficiency property holds also for Bayesian inference, though we shall defer discussion of this until chapter 8. Okay. So yeah, so I think it's this notion, and we saw this in 2 videos ago when we were talking about the cool things about the exponential family, was that they have this this notion of the sufficient statistic, where the data only affects the parameters through this sufficient statistic, and that can kind of serve as a kind of a compression, a lossless compression of all the information you need to determine that parameter. And we can see that here, that the way to figure out, what the parameter is by computing the average of this sufficient statistic, and that tells you all you need to figure out, eta of ML. So that's what that's about. Okay, so then let's just go on to this section on conjugate priors, which is pretty straightforward. Okay, so remember the idea with the conjugate priors was that when you have a likelihood, you combine it with a prior to get your posterior, and if your likelihood will have some form, and if your prior is in the same family, then when you multiply them together, then the posterior will be in the same family. So the conjugate prior is a prior that has come in the same form as the likelihood. And that can be useful, make your calculations simpler. It can also be useful for intuitive reasons, for like making it easier to see like what the parameters mean and how they update, etc. So we've already kind of talked about this a little bit. So hopefully you remember that from our previous discussions. Now we have already, what does it say? So we have already encountered the concept several times. Indeed, for example, in the context of the Bernoulli distribution, for which the conjugate prior is the beta distribution, or the Gaussian, where the conjugate prior for the mean is Gaussian and for the precision is the Wishart. In general, for a given probability distribution, we can seek a prior that is conjugate to the likelihood function, so the posterior distribution has the same functional form as a prior. So this is just what we just said. Now, it's going to be pretty easy for the exponential family. We just pick a prior so that when you multiply, it kind of has the same form as the exponential family itself, right? So just to again remind you, for the exponential family, it was, we had h of x, and then we had g of eta, and then we had exp times u of x, right? So we're just, essentially the whole game is going to be like making the prior so that when you multiply by a term like this, the result also looks kind of, has the same form. There exists a conjugate, so for any member of the exponential family, there exists a conjugate prior that can be written in the form this. So this is the prior, and these are chi and nu are, I guess they're going to be the hyperparameters that are going to be your priors on your parameters. So the parameters of your prior distribution, basically. So now you have this f of x of nu, g of eta to the nu, and then you've got this exponential term. This is the normalizing coefficient, so this is going to normalize over your prior parameters. G eta is the same function as appears in 2.194, so let's just, that's important. To see that this is indeed conjugate, let us multiply the prior 2.229 by the likelihood function 2.227. So whereas, I guess that's this one. I wonder if that's the one he means. Yeah, he does. Okay, because we've got these sum of these terms. So imagine you've got this likelihood now coming in, and now you're going to multiply it by prior, by your distribution on your prior, to get a posterior on your parameters, and you want them to be kind of in that same family. So when we do that, what do we get? Well, you get the g of eta. There's the n points coming from your observations, and then you've got the nu coming from your prior. And then you've got the term showing up in the exponential. So this is again being contributed by your observations, and you've got something else contributed from the prior. So it looks like, again, it's in the same family. So that's kind of pretty straightforward. This again takes the same functional form as the prior 2.229, confirming conjugacy. And then we played this game already to some extent. We see that the parameter nu can be interpreted as an effective number of pseudo observations in the prior, right? Because we had n observations, and now we're adding nu to it. So it's almost like that's kind of the number of pseudo observations that we had, each of which has a value for the sufficient statistic u of x given by chi. So this is, imagine you've got, that's just saying that this is equal to the sum on chi where and you're summing, I is equal to 1 to nu, say. So, that you can kind of use this conjugacy to interpret what these parameters mean. So this is going to be your effective number of pseudo observations for your prior, and it's going to be the corresponding value of the sufficient statistic for each one of those each one of those pseudo observations, which you assume is going to have the same value. Okay, so that's it. So I think we just kind of covered these two basic properties. I think this conjugate property, conjugate prior one, is pretty straightforward. It's cool to know about it, and it's just you just pick the form that puts when you multiply it by the form of the exponential family, the likelihood brings you back into the family, keeps you in the family basically. And then there was this interesting property here, which I don't have any intuition for, but that basically the moments of the sufficient statistic can be determined from the gradients of the normalizing function. So if any of you guys have intuition for why that is, just let us all know. That'd be very useful. Good. So hopefully that was useful. You learned something about the exponential family. The very next section, we're going to be talking about non-informative priors. That will be the end of our discussion about the exponential family. So hope to see you then in section 2.4.3.